All right, so one thing I want to mention about the material we've been doing, and in particular about the Cauchy-Euler equations, so equations that look like this with matching powers of t to the number of derivatives like we have here, is that there's actually another way we can get the particular solution over here. But anyways, the way we get the homogeneous solution, which we should always do first because that can affect the particular solution, is we look at this certain polynomial. And the polynomial looks like this. So we take the numerical, not the t's, but the numerical coefficients of these y's and their y primes, and we stick them in here and make a polynomial out of it. So there's just nothing, no number in front of here, so that's going to be r squared. B is 1, but then a is also 1, so this will be a 0, and then we have minus 4 here, and then that equals 0. So the powers of t that are going to be in our homogeneous solution will be plus or minus 2. So our homogeneous solution YH is going to be C1 t squared plus C2 t to the negative 2. So that would be the solution to this stuff equaling 0. But the thing is, we don't have it equal to 0. We have it equal to t cubed. Now, in the lectures, you were taught that with the Cauchy-Euler equations like this, the only way to do the inhomogeneous part is by doing variation of parameters. But that's not entirely true. It turns out we could do undetermined coefficients for some instances with this too. So what I'm going to do is I'm going to assume that my solution will look something like that. So I'm going to assume my yp will be at cubed. And then I'm going to plug this into here and then see what a has to be for this to work. So my yp prime will be 3at squared. My yp double prime will be 6at. All right, so now we have that, then we could plug that into here. So if this is a Cauchy-Euler equation, these powers of t's will make it so all of these will end up having the same power of t. It should match up to what we have over here. So for example, my yp double prime, let's see, that will turn into a 6a and then t cubed. And then I have plus t times y prime, so that'll be plus 3a t cubed. And I have minus 4 times y, so minus 4a t cubed is t cubed. So then I'll notice that all of these are t cubes and the coefficients need to match the other side. So that's going to tell me, let's see, I have 6 plus 3 is 9, minus 4 is 5. So I have 5a t cubed is t cubed. That means that 5a has to be 1, or in other words, a has got to be 1/5. So my complete solution, which is the homogeneous plus the particular solution, will end up being c1 t squared plus c2 t to the negative 2 plus 1/5 t cubed. And notice how I was able to figure that out. And I didn't need to use variation of parameters at all. So in particular, if you have a Cauchy-Euler equation and you have something over here that looks like something you could get from a homogeneous solution, like a power of t, then you can actually use undetermined coefficients with this too. I want to make sure you guys knew that because I don't think they mentioned that in the videos of the lectures at all. One caveat I want to go over though, and this is a little bit different from how undetermined coefficients worked before, is let's say I change this equation. Let's say instead of doing this with the t cubed, that instead I have t squared right here. So let's say I just modify the inhomogeneous part to be t squared. Now remember, the homogeneous part will be exactly the same. So we still have YH, C1 t squared plus C2 t to the negative 2. Now you may remember for undetermined coefficients with the constant coefficient equations, like the things we did a little bit earlier, when we have this being similar to one of our other functions we have for the homogeneous solution, we need to modify it a bit. So it's what's called linearly independent from it. Now, in that case, we added a power of t. So we stuck powers of t next to exponentials, sines, and cosines. But for Cauchy-Eulers, what we do is rather than sticking powers of t there, we stick powers of logs there instead. So my yp won't just be at squared, it'll be at squared times ln of t to the first power. And maybe if I already had like a t squared and an ln of t squared right here, then in this case, I would square my log to avoid overlap for that case. So we don't add powers of t when we have overlap for Cauchy-Euler, we add powers of logs. Now, if all of this sounds like, oh God, I don't want to learn another method or anything, that's totally fine. You can just use variation of parameters on these problems and it will totally work out, so long as you don't forget to divide by this guy. I just that personally, I don't like variation of parameters because you have to do at least 2 integrals and they tend to not be very pleasant. So I try to avoid using variation of parameters if there's another alternative. And undetermined coefficients is usually a better alternative to variation of parameters when you can get away with it. But just like the other situations, if we have like tangent of t over here or something like that, then we have to use variation of parameters because that doesn't look like anything we can get from a homogeneous solution. So sometimes we have to do it no matter what, but sometimes we can avoid it. All right, that was kind of the big thing I wanted to say before we get started. I know you guys probably have a lot of questions about the practice exam or other things. So yeah, I'm going to open it up to you guys now. Feel free to ask any questions you have. And it looks like we have a lot of people here today. So if we don't get to your question right away, please feel free to type into the chat. I'll try to get them in the order that I received them. So hopefully we'll be able to get to everyone's questions. So yeah, I'm opening it up to you guys. Do you guys have any questions on any of the material for Module 3?
Could you go over question 6 from the practice exam?
Yeah, sure. I have it pulled up here. Let's see. Question 6. Okay, so this one's about finding a particular solution to the given differential equation. So let's see what equation that is. Okay, so in this case, what do we have? We have y double prime minus 5y prime plus 6y is t times e to the t. Okay, so first what we need to do is we need to solve the homogeneous equation to see if that looks like the thing on the right side, because if it does, we need to modify our guess for what the particular will be on the right-hand side. But if it's different, then we could use our normal undetermined coefficients. So the associated polynomial for this will be r squared minus 5r plus 6 is 0. And I'm pretty sure this guy factors. This will factor into r minus 6 times, oh wait, what am I doing? That's not true. It'll be r minus 2 times r minus 3. There we go. Oh, I need to go back to algebra. Yeah, so we have r minus 2 times r minus 3. So that means our r will be 2 and 3 here. Now, thankfully, if we got an r value of 1, we would have to worry about overlap because that would give us e to the t's. But since we don't have that, we're in the clear. So our homogeneous part, which we can forget about after I write it down now, looks like this. And since we have e to the 2t, e to the 3t, and not e to the t, then we don't have to worry about overlap. All right, so now what are we going to do? Well, this guy is a product of polynomials and exponentials. And whenever we have some combination of polynomials, exponentials, or sines and cosines, where they're multiplied or added together, we can do undetermined coefficients. So I'm going to do that in this case. I always prefer to do that when I can. So I have t e to the t here. Okay. So what does that mean about yp? Well, I definitely have to have a term that looks like that. But anytime we start with a higher power of t, I need to keep going down all the powers of t until I have t to the 0 or no more t's. So it's easy to forget that we also need a b e to the t there as well. It may seem kind of strange because we don't have that. And here there's no constant e to the t, but you still might have one in your solution. All right, then as usual, we take 2 derivatives of this so we can plug it into the equation. So let's see, yp prime. I'm going to have to do a product rule here. So I get a e to the t plus at, e to the t plus b e to the t. So that's what I get when I do the product rule on this. And then this is its own derivative. And then going to do this again here. The derivative of a e to the t is a e to the t. The derivative of this is exactly the same as what I got here. So that's just going to add another a e to the t, a t e to the t, And then we're still dragging along this b e to the t, which is its own derivative. All right, so now we have all of our derivatives computed. Hopefully you guys can, let me know if you guys can't see this up here. I'll try to write a little bigger. So we have all of our derivatives computed, and then now we're just gonna plug them into our equation, see what a and b have to be. All right, so let's see here. So we have y double prime. Okay, so this is really just 2a e to the t, so I'm gonna write it like that. So I have 2a e to the t plus a t e to the t plus b e to the t. So that's my y double prime. And then I subtract 5 times this right here. So I have minus 5a e to the t minus 5at e to the t, and then minus 5b e to the t. And then finally, I have plus 6 times the original one. So I have 6at e to the t plus 6b e to the t. And when you add all of that together, we end up getting just t e to the t. Okay, so whenever we get equations like this, the way to think about these is that this function right here, this kind of compact little function, t e to the t, is exactly the same as this kind of messy looking function over here, meaning the coefficients of all the t e to the t's on this side need to add up to 1. And if we have any just e to the t's, they need to add up to 0 because we don't have any e to the t's here. So that should give us enough equations to work with. So let's gather together all of the ones without an extra t. So it looks like it's going to be 2a for that one, plus b minus 5a minus 5b, and then plus 6b. So all that stuff, that's got to be 0. And then let's see what the other equation is with t e to the t. So we have just one of them here. So we have a, and then we subtract 5a of them, and then we add 6a. And then all that has to equal 1 because we have one of these t e to the t's over here. Now I'm definitely going to look at this equation first because this one looks a lot easier to solve than this one. So I have 1 minus 5 plus 6 is going to be 2. A is 1, meaning that a has got to be 1/2. That means our a is going to be 1/2 here. And you can kind of look at the multiple. I don't know if you guys have multiple choice stuff. That immediately eliminates 2 of these answers. It definitely can't be 3/4 t e to the t. So it eliminates 2 of them right away. And then we can go back up here. Let's see if I combine all of the coefficients together that match. For this one, I end up getting, let's see, 2a minus 5a is negative 3a. And then with the b's, I have b minus 5b is negative 4, and plus 2b is 0. So I could add this 3a over here, but that's really 3/2 because a is a half. And then I could divide by 2. So b ends up being 3/4. So that means my particular solution, now that I have both these, is going to be 1/2 t e to the t plus 3/4 e to the t. And I think all of these ones end up factoring their answer. It looks like, yeah, I don't know. I mean, may have shuffled them for you guys, but it looks like the 4th answer is the correct one here. So sometimes they factor their answer, so you may need to do that too. Usually you can just pull an e to the t out of everything, and then it should be good. All right, but the kind of moral of this story is that even though we didn't have a regular e to the t in our right-hand side in the beginning, we still end up with an e to the t in our yp. So don't forget to include that b e to the t term. That was important for solving this. All right, let's see. So does anyone have any other questions? And feel free to put some in the chat while you're waiting. It's okay if you do it while I'm talking. We can get to them after I'm done answering the current question. Does anyone have any other things you'd like to go over? I have a question. Does the practice exam count for a grade? And no, so there isn't any extra credit from the the practice exams. So yeah, so you could do them for practice. I mean, that'll definitely help you on the real exam. They're pretty similar, but yeah, there's no extra credit from those, unfortunately. Let's see. Anyone have any other questions on like variation of parameters or distance and uniqueness? Let's see. Will there be any questions like number 7 on lecture 15 homework? Well, let's see what that is real quick. All right, let me pull that up. Lecture 15, that was superposition. All right, number 7. Okay. Yeah, I can see why you might ask about this one. So let me only show you guys what this equation is here. So for this one, we have y double prime plus 16y prime plus 65y is going to be 6e to the negative 8t cosine of t. All right, and we want to figure out what the solution to that is. So let's look at the homogeneous solution here, and I think we'll see why this one's going to be a little bit nasty. So let's see here. I'm pretty confident that this one doesn't factor nicely, so we need to use the quadratic formula here. So we have negative 16 plus or minus the square root of 16 squared, or 256, minus 4ac. So that's minus 260 all over 2. And when we simplify this, 256 minus 260 will be negative 4, and the square root of negative 4 will be 2i. So this will be negative 16 plus or minus 2i over 2, but then that simplifies to negative 8 plus or minus I. Now, unfortunately, if you see that, what that means is that our homogeneous solution to this equation is going to look like YH will be C1 e to the negative 8t cosine of t plus C2 e to the negative 8t sine of t. Okay, well, that's not ordinarily so bad if it were just a homogeneous equation, but if you wanted to do undetermined coefficients, unfortunately, this looks very similar to what we have here. So we would need to bump up this by a power of t, meaning we need to do 2 sets of triple product rules when we do the derivative. So needless to say, this is a very tedious problem. Don't worry about a problem taking up all your time like this on the exam. They're not going to be that way. Now, one thing that could happen, though, is we could give you a problem like this, and we could be like, okay, write down the form of the particular solution. So you write like AT e to the negative 18 cosine of t, and so on. And you would just write those down, but then you don't have to find the coefficients, because that'd be very tedious to do that. So that's definitely possible, but yeah, the problems won't be so tedious. You'll be spending like 45 minutes on one of them or something. So don't worry about that. All right, so let's see here. Can we go over number 18 on the practice exam? Absolutely. Let me get down to that one. Okay, so this one has to do with reduction of order. So sometimes you're able to find one solution to a differential equation, but if it's second order and it's linear, you're guaranteed to have 2 linearly independent solutions. So how do you find the other one? Well, reduction of order gives us a way of doing that. Unfortunately, involves a lot of integrals. So that's the downside. So for this equation, we have ty double prime minus 3t plus 1 y prime plus 3y equals 0. Okay, and they were kind enough to give us one solution to this. It's just going to be y1 is e to the 3t. And from this solution, we need to get another linearly independent solution. Okay, so what's going to happen with this? Well, in order to use this, and also in order to use variation of parameters, we need to make sure that our coefficient in front of y double prime is just 1. Like there's nothing sitting there like that t, for example. So the very first thing we need to do is just divide everything by t. So we have y double prime minus 3t plus 1 over t, y prime plus 3 over t, y is 0. Now, I would say in particular for these, God, I'm blanking, reduction of order problems, I would say for those, be very careful about your signs. Because first of all, so that negative there, it's really easy to just drop these parentheses and have negative 3t plus 1. But that's not entirely right, so watch out for the negative there. Another reason to watch out for negatives is that our y2 will be y1 times the integral of e to the negative integral of p dt divided by y1 squared. So don't forget about that negative that comes in the formula for reduction of order as well. It's easy to forget about that too. So we're going to use this formula. And by the way, p is whatever is next to the y prime after you divide by the t. Okay, so let's go ahead and do this. So that's why I was saying there's a lot of integrals, because you have to do the integral just to get the function inside another integral. So yeah, it's unfortunately not too pleasant. Sorry, so that means in order to get what's in this exponent right here, we need to do negative the integral of this. So the negative will cancel out with this negative here. So we're just doing the integral of 3t plus 1 over t dt. Now for some of these, you might need to do a U-substitution, or you could be clever and do like the kind of +1 -1 trick as well to do a lot of these. Thankfully for this one, since it's just a t on the bottom, we can just divide both those terms by t, and that'll be totally fine. So we have the integral of 3t over t is just going to be 3. And then I have 1 over t dt. And then thankfully, those are both pretty easy integrals to do. So we have 3t plus ln of t. And they say in the problem that t is greater than 0. So we don't need to worry about the absolute values on that natural log. All right, so remember, this is what's going in the exponent. And then we need to do another integral. So get rid of that. This is going to turn into y2 is y1. By the way, y1 was e to the 3t. And then we have the integral of e to the 3t plus ln of t. That's what we got. And then we have our y1 squared. So that's e to the 3t squared. That will be e to the 6t. As powers in exponents turn into multiplication. E to the 6t. Okay, and a lot of times these integrals will be mostly the same. You're going to have some weird exponentials, but then you just use exponent laws to simplify everything down. That's exactly what's going to happen here. So I have e to the 3t out here. Now remember, addition inside my exponent turns into multiplication outside of the exponent. So this is e to the 3t times e to the ln of t. But remember, e and ln, they sort of cancel out with each other. They're inverse functions. So that's just going to cancel out to be a t. So we have e to the 3t times t, and then we're still dividing by e to the 6t. Like that. All right, so we have that, and then we're going to simplify this now. And then it'll be an integral that we're confident in doing. So this will be e to the 3t. E to the 3t divided by e to the 6t will turn out to be e to the negative 3t times t. And then now we're sitting pretty here, because once we have an exponential times a polynomial, then we can use integration by parts, or the tabular method as it's also called. And we'll definitely do the table for this, because it is a polynomial times exponential. It's one of the best times to use the table. So here's our derivative column. Here's our integral column. We're definitely going to put the polynomial in the derivative column. So we have t, 1, and 0. And we have e to the negative 3t, e to the negative 3t over negative 3, e to the negative 3t over positive 9. And then we multiply these together and attach signs to them. Okay, well, what's going to come out of that? Well, I can actually write my answer down here. So remember, this is the e to the 3t that was on the outside. And then I have these guys multiplied together, so that will be negative 1/3 t e to the negative 3t. And then I have this term as well. So that's minus 1/9 e to the negative 3t. Okay, and then finally, what typically happens with these reduction of order things is that oftentimes the y1 out here will cancel out with a lot of the stuff that you get from your integral, and this one's no exception. This e to the 3t will cancel out all of these exponentials, and so we end up getting, for this one, we have just negative 1/3 t minus 1/9. And thankfully, that is one of the answer choices here. So that's going to be our solution for that. So reduction of order, it's just a bunch of integrating. And like I said at the beginning of the semester, we're just going to be doing a lot of integrating and a lot of guessing this semester. And we've done a lot of both in this section. All right, let's see. Got a few questions while we were doing that one. Let's see. All right, so we have a question from Georgia. When you find R1 and R2 for the homogeneous solutions, does it matter which R goes with C1 and C2? And the answer is no. You could put them in either order you want. It doesn't really matter which way you do it. So you can make either one be C1 or C2, and it's fine. Now, if they give you a homogeneous solution to use to do something, like they say, oh, here's the homogeneous solution, find the particular one using like the Wronskian or something, then I would probably stick with the way they assigned it because the answer choices will probably be consistent with that. But if you're just writing down your own things, then it doesn't matter which way it goes. All right. Let's see. So can we do number 8 on lecture 15? Absolutely. All right. Is this lecture 15? Yeah, okay. Oh, it was the one after we did earlier. Okay. Yeah, so this one has a little bit of weird variables, but you know, still going to be the same procedure. So let's see. So we have z double prime plus z is equal to 8 e to the negative 2x. So it appears that z is going to be the dependent variable here, and x is going to be the independent variable. By the way, one thing I had to do when I was a math major is that it's really easy to make a z look like a 2 if you don't put this line through it. So I suggest if you ever have any problems with z's in them that you're using math, try to put this little line through it. It'll make it easier for you to read. I had to train myself to do that by like writing 100 z's in a row. Yeah, so get used to that early because it's really easy to confuse them if you're writing them out. All right, anyway, so we need to solve this. Oh, and they also give us initial conditions. So this is an initial value problem. We have z of 0 is 0, and z prime of 0 is 0. Okay, now normally if we didn't have anything over here, if this was 0, then the solution would just be 0 right away because everything would just 0 out. But since we have this inhomogeneous term, it won't exactly just be 0. Okay, so as always for these, we first need to solve the homogeneous problem, and then we solve the inhomogeneous part, or by finding the particular solution. So let's see, so the polynomial for this will be r squared plus 1. Now, one thing I got tripped up on when I was taking this class is that it's really tempted to, especially when you don't have a middle like single prime term, to put like r squared plus r because this is like a z, so you think there should be a variable down here. But remember, if there are no derivatives on it, then there's no variable down here. The power of this r is the number of derivatives. So that's why this will just be a 1. So that's kind of an easy little slip up. So watch out for that. All right, so we have r squared plus 1 equals 0. Well, this is a pretty famous equation because the only way we can square a number and get negative 1 is if that number is plus or minus I, the imaginary u. All right, so what does it mean when we get an imaginary solution to this polynomial? That means we're going to have sines and cosines as part of our answer. And if we have a purely imaginary result like this, like there's no number in front of here, there won't be any exponentials at all. It's just going to be sines and cosines. So our ZH will be C1, and then the coefficient of this I right here is going to be the number inside the sine or cosine, but that's just a 1 here. So it's going to be cosine of x plus C2 sine of x, like that. And as I said earlier, it doesn't matter which one I put first. You can put sine first if you want, then cosine. Doesn't really matter at all. All right, so there's our homogeneous solution. And thankfully, cosine and sine aren't that similar to e to the negative 2x. So we can use undetermined coefficients without having to bump anything up by t's. That's going to save us some time, thankfully. Okay, let me erase this and keep my initial conditions because we're going to need those. So my ZP, that's definitely going to be A times e to the negative 2x, because that's what my right-hand side looks like. I'm going to do two derivatives of this so we can plug it in. I have negative 2a e to the negative 2x. And then ZP double prime will be 4a e to the negative 2x right there. All right, so then we just go ahead and plug those into the original equation, which I erased, but it's just z double prime, which is this, plus the original z. And that had to be, I believe, 8 e to the negative 2x. All right, and as we've done with undetermined coefficients in a few of the problems we did earlier today, we just kind of combine like terms and then match them up with the other side. So I have 4a plus a, that gives me 5a, and that's got to be 8. So I have 5a is 8. So my a has got to be 8/5. So that's going to be my particular solution. All right, so my general solution, which is the homogeneous plus the particular one, is going to look like this. Going to be z is c1 cosine of x plus c2 sine of x plus 8/5 e to the negative 2x. Now the thing is, we'd be done normally if they didn't have initial conditions, but this one does have initial conditions and it needs 2 because we have 2 derivatives. So we're going to plug those in and then we're going to get specific numbers for our coefficients for C1 and C2. All right, so the first one we have is z of 0 is 0. All right, so that means that we have 0 here for z, and then we have c1 cosine of 0. Well, cosine of 0 is 1, so we just have c1. And then we have c2 sine of 0. Well, sine of 0 is going to be 0. Oh, we have a comment here. Oh, so when you solve for c1 and c2, you include the particular solution. That's right. Actually, if we didn't include this particular solution, what would happen is that these would end up just both going out to 0. So it's really the particular solution that enables us to get something meaningful here. So we do need to include that when we're solving for those. All right, so let's keep doing this. It's going to be a little bit messy with algebra, I bet. We put 0 in here, and then we get 8/5. All right, so then I subtract that over. Actually, this one wasn't too messy. We get c1 has to be negative 8/5. All right, then the unfortunate part about higher order equations is that the initial conditions involve derivatives. So we need to take the derivative of our solution and then plug in the numbers. So z prime will be, the derivative of cosine is going to be sine, or negative sine. We already know what c1 is. That's going to end up being 8. Oh, wait a minute. Sorry, let me not skip ahead. So we have 8/5 sine of x for that. And the negative here went away with the negative from the derivative of cosine. And then we have c2 cosine of x. And I do the derivative of this. I got negative 16/5 e to the negative 2x. All right, so now that I did that, I'm going to go ahead and plug in my, my 0 for everything, because z prime of 0 is also 0. So I have 0. It turns out it didn't matter what that number was at all, because sine of 0 will just be 0. Again, we have cosine of 0, which will be 1, so I have c2, and then e to the 0 will be 0, and then we have my negative 16/5. So it looks like c2 is going to be 16/5. Now, it didn't matter originally which one I said was next to sine, which was next to cosine, but the only time it does matter is once we find the numbers, because then, no matter what I did, this 16/5 has got to attach to this sine, and that negative 8/5 must attach to the cosine. No matter which way we started it, those specific numbers need to be matched up to the appropriate function. So our final solution here is z is negative 8/5 cosine plus 16/5 sine plus 8/5 e to the negative 2x. And there we go. And with initial value problems, we don't want any undetermined constants left over. So it should be all numbers and functions. All right, so that's good. That's an initial value problem. It's just mostly just a normal problem, but then with a little extra algebra at the end. Let's see here. Let's scroll up a little bit. All right, so we have some extra questions here. So on lecture 15, number 10, okay, how do you know to add CE to the 2t? So for that one, I like to think of doing undetermined coefficients. It's kind of looking like breaking up your right-hand side into chunks. So let's take a look at that real quick. And this will actually have something to do with number 9 as well. So hopefully this will get everything in one go. So anyway, so for number 10 from this, we have y double prime minus 10y prime. My 10s keep looking like 16s. There we go. Minus 10y prime plus 26y is, and then we have a long right-hand side. E to the 2t plus t sine of 5t minus cosine of 5t. Okay, so the way I like to think about undetermined coefficients and knowing which things to include is I like to kind of break up the right-hand side by what roots of the polynomial would make me have that function. So let's say that I solved some kind of homogeneous problem and I ended up having an e to the 2t as one of my like C1, C2 homogeneous solutions. Then what R value would I have gotten to have e to the 2t? The answer is R equals 2. So in order to have this guy in here, I would need to have R equals 2. So I like to kind of think of that as one thing I need to do. And then for these two guys right here, they actually come from the same root. This would come from R is plus or minus 5i, because that gives me sine of 5t and cosine of 5t. But since we already have a t there, it's like we got that more than once. So this is kind of like a double root. So we're going to have two of those, meaning we need to have a t next to them, and then we just have the constants. But we need to have one for each, what I like to think of as family for this. So our yp will end up looking like a e to the 2t. So I managed to get this guy. And then since I have a double for this because of this t, then I'm going to have bt sine of 5t plus ct cosine of 5t plus d sine of 5t and then plus e cosine of 5t. Because normally if I were doing undetermined coefficients and I got plus or minus 5i, I would have sine and cosine. But since I have a t there, that means I got them more than once. So I need to have t's for them as well. So this would be what my yp would look like. So this is what yp would look like if it doesn't overlap with the homogeneous guys over here. If it does, like maybe I did get r equals 2 or r is plus or minus 5i over there, then I would need to just tack on a t to every member of the family that appeared over here so there wouldn't be overlap. So hopefully that kind of makes sense. If you start working through these, you'll eventually start to get a feel for how this works. It just takes a little bit of experience. Let's see here. So Yaru, you might have answered this already. So as far as knowing whether to use undetermined coefficients versus variation of parameters, my personal choice is just use undetermined coefficients when you can, because most of the time it's a lot faster. It's much easier to do 2 derivatives and plug something in than it is to do 2 probably complicated integrals. So I always prefer to use undetermined coefficients. The downside to that method is that it's not as versatile as variation of parameters. Variation of parameters, you can do anything. You can do any function that shows up on the right-hand side. But for undetermined coefficients, you can only do functions on the right-hand side that could have showed up as a homogeneous solution over here. And for the equations look like this, the constant coefficient ones, that's just only going to include exponentials, sines and cosines, or polynomials, or any multiples or additions of those, but not divisions. You can't divide those. So pretty much I try to use undetermined coefficients anytime I have polynomials, exponentials, sines or cosines, or multiplied together. But if it's anything else, like if it's like tangent of t, ln of t, like 1 over t squared or something, in those cases I have to use variation of parameters because there's not really a choice there. So the moral of the story is use undetermined coefficients when you can. It's almost always faster and easier. But sometimes you have to use variation of parameters for things that look kind of strange. So that's kind of my basic synopsis of that. And you're welcome to ignore that, of course. You could technically use variation of parameters on every problem, but I don't know about you, but I think integration tends to be more difficult than differentiation. So I always prefer to avoid integrating stuff when I can. That's my sort of long answer to that. I think we exhausted the list of questions here. Does anyone have any other questions or any other topics you'd like to discuss? Anything else that seemed tricky or difficult or you want to go over? All right, well, if no one has anything right now, and you could feel free to interrupt me and like type something in there. I want to get a little bit more practice with the undetermined coefficients, or at least setting them up. Because I think it's kind of confusing at first. So let me try to come up with a problem that's kind of enlightening for that. So how about we do, let's see. How about this? Y double prime plus 4y prime plus 4y is t cubed e to the negative 2t plus e to the negative 2t sine of t plus t squared. There we go. Okay, so this should cover pretty much anything that can happen with undetermined coefficients. So this one, now we're definitely not going to finish this problem. This right-hand side is pretty horrendous. I'm just going to try to set up the YP for this one. So, and that's definitely I mean, you've done the practice test. I'm pretty sure we had a few of those in there. Yeah, determine the particular form of the solution. Definitely know how to do something like this. Something like this could very well show up on there. You won't have to do the whole thing because it'll take forever, but you may have to set up YP. Now, the first thing we need to do before we do any of the YP stuff is we need to find our homogeneous solution. So that's going to be r squared plus 4r plus 4 is 0. And then if I look at this and I factor it, that's going to give me r plus 2 squared is 0, meaning that we get r is negative 2. And it may seem kind of dumb, but I'm going to put negative 2 twice. It's a repeated root. And it actually makes a difference. Remember, if we get a repeated root on this side from our polynomial, then we need to stick an extra t next to it when we're writing the homogeneous solution. So our homogeneous solution here will be c1 e to the negative 2t, because, I mean, we got negative 2, but we also need c2 t e to the negative 2t. We're going to have that as well. Now, we need to define the homogeneous solution because, remember, something that appears in here, like one of these kind of functions, can't appear in YP. The reason is if we include it in YP, it'll just go to 0 when we put it in the equation anyways, so it'll be useless. So we don't want either of these to show up in YP. All right, now let's write out what YP would be if we didn't know what the homogeneous solution is, and then maybe we can tweak it to fix it once we're done. So my first term here is this t cubed e to the negative 2t. So I'm going to try to apply my reasoning from the last issue I talked about to see how we would break this up. So I have e to the negative 2t here. So what root would that come from? Well, that comes from r is negative 2. But since I have t cubed here, that means I need a copy for t cubed, t squared, t, and then just a constant one. So that'd be like a negative 2 root, and then we have 4 of them. So my YP so far would be a t cubed e to the negative 2t, and then b t squared e to the negative 2t, ct e to the negative 2t, and then d e to the negative 2t. Okay. Now, one thing you might observe here is we have e to the negative 2t here, but then we also have it there. Why didn't I consider that? Well, technically, that comes from a different root. So what root would this guy come from? This one would come from negative 2 plus or minus I. So anytime we have a sine or cosine, that means we had an imaginary root. And since there's no coefficient here, it's just going to be I. But then when we have an exponential multiplied by it, we have a real part as well. So this one comes from the root -2 plus or minus I, which is different from that one. And thankfully, we only have one of these. There are no t's or polynomials attached to that. So we're just going to have e to the -2t sine of t. And then whenever we have sine, we have to have copies for cosine as well. Reason being is that we have plus or minus. One of them corresponds to sine, other one corresponds to cosine. All right, so we took care of this part, we took care of this part, and then we just have a t squared on its own. So kind of following along with this root business, so we have -2 is the root that would make that. -2 plus or minus I would make this one. Can anyone type in the chat box or say out loud what root would give me just a t squared with no exponential or sign or anything? Pretty simple number. What R value would correspond to just a t squared on its own? That's okay if you guys are feeling a little shy. So here's a hint for this. So let me write this a little further down. So I can always stick a 1 next to things, right? So the 1 I'm going to stick next to here is e to the 0 t. And that's okay to put there because that's 1. So technically, this t squared comes from the root r equals 0. And since it's a t squared, that means I need to have a term for t squared, t, and then a constant. So if I continue going with this, I have g t squared plus ht plus I at the end. So this one corresponded to r equals 0, and we have 3 of those, so it's times 3. We have 3 of those roots. I don't know. This is the way I usually think about it with breaking this stuff up. Hopefully this makes at least some amount of sense. The main point is that you need to look at these in terms of families. Now we're not entirely done here because we do have overlaps. So notice how I have a constant times t e to the -2t, and then a constant times e to the -2t. But the thing is, I already have that for this YH, right? So we can't have any overlap with that. So what we need to do is we need to bump up that particular family by powers of t until there aren't overlap anymore. Now, if we just bump it up by 1 power of t, we'll still have t e to the -2t, and that will match up there. So we need to bump up everything by t squared, so there's no overlap. So this would be a t to the 5th. This would be b t to the 4th. This would be ct cubed. And then this part would get a t squared. And then now we don't have any overlap. And in this case, even though we end in t squared, since we got that from bumping it up to not overlap here, we don't put t or the constant anymore, because that would just overlap with this again. So you need to bump up things by t, but only in that particular family. Like notice I didn't change any of this other stuff. I only bumped up the things that just had e to the -2t when we have overlap here. So it doesn't apply to everything. We only need to bump up certain things by t. So that's the kind of way of thinking about it. Superposition is just a fancy word for breaking things up into families and making sure you have coefficients for each one of those different families. So that's what's going on there. Hopefully that made some amount of sense. Once you get more practice, undetermined coefficients is definitely the way to go. I'm pretty sure you've done some of those integrals. They're not super pleasant. I will say though that the integrals won't be like insanely long, and this won't be insanely long either. We won't have like 9 terms for your exam. I guarantee you won't have 9 ones you actually need to solve for. So you don't worry about that. But I don't know. This tends to be easier in practice than variation of parameters once you get good at both. All right. So I don't want to talk. Does anyone else have any other questions or concerns or anything you'd like to ask? Everyone's okay? Everyone's feeling pretty good about this? The second exam tends to be a bit harder than the first one just because I think second order equations are a bit harder than first order ones. I mean, they definitely take longer, that's for sure. But I don't think this exam will be anything that's going to be like crushing or anything like that. Let's see, could you go over harmonic motion? So you're talking about like springs and that sort of business. Yeah, we can talk about that. The main thing about these springs is that they just end up being a constant coefficient second order equation. So the form for that is going to be mx double prime plus, usually they use b for this, x prime m plus kx equals 0. And I'm just going to straight up tell you right now, we're not going to have any of the forced motion for springs. They may have talked about that in the lectures and the notes a little bit. We're probably just going to focus on when they're going to be, when we're going to have a coefficient of 0 over there. So that don't worry too much about that complicating things. Now, the main thing to get out of this spring motion stuff is it's just like a second order equation. You just plug in particular numbers for these. And this is the mass, this is the dampening, and then this is the spring constant. And so if you put all those in there and then write out the associated polynomial, which is mr squared plus br plus k, then you could end up solving for the motion of the spring. And remember, there are a few different types of motion for this. So there is undamped, underdamped, critically damped, and overdamped. So there's 4 different types. Let me kind of go over each one briefly. So undamped is where you don't have any dampening at all. So this would be like if your spring was like oscillating in space or something like that, where there's no there's no like air resistance or liquid or anything like that. And that's just when your B equals 0. And for that case, your motion will just be a constant sine or cosine function. By the way, I've had some people ask if you would have to convert sines or cosines into just one sine with like a phase shift or something like that. Don't worry about that. You won't have to do that either. But if you have undamped motion, it'll just be pure sine or cosine motion forever. Underdamped is where you have some dampening, but it's not a lot. And what I mean by that is that b squared is going to be less than 4mk. So that's what I mean by a lot. Your b squared is going to be less than this number. And what happens is since you have dampening, but it's not that much, we're still going to kind of bounce up and down, but it's going to kind of flatten over time. That's because the dampening is removing energy from the system, and it won't be able to oscillate as much as we go on. So kind of a good example of that is like if you like shove a swing really hard or a pendulum, it'll kind of swing freely for a while, but then its oscillations will get shorter and shorter and shorter, and then finally it'll look like it'll stop. That's an example of underdamped motion. Critically damped, and then the next two are very similar to each other. It's kind of hard to tell the difference. Critically damped is where b squared exactly equals 4mk. And of course, in practice, since real numbers that you encounter in the world go off to however many decimal places, this is kind of like an ideal. But if you do happen to get b squared exactly equal to 4mk, what you end up getting is something that kind of looks like this. It looks like pure exponential motion, and it'll go off to 0. Now, the defining feature of critically damped versus the next one, overdamped, which is where b squared is greater than 4mk, the graphs look almost identical, but the difference is that overdamped springs, or systems in general, they'll have the same shape as this, but they'll go to 0 more slowly than critically damped systems. In fact, critically damped systems, the advantage of those is that they go towards 0 the fastest out of any of them. So if you want your function to go to 0 really quickly, then do critically damped. But overdamped, your dampening is so heavy, imagine like your spring's going in molasses. It's just slowing it down so much that it could barely even get down to equilibrium. So that's what's going on with the 4 different dampenings. So I would definitely recognize how to tell at least these two from the other two on a graph. I don't think I'll have you guys tell the difference between these two. It's really hard unless you see the specific equations. So these two are effectively the same in terms of the graph, but I think you should at least know the difference between these graphs and then the other two, which I just had up there. All right, that's pretty much all you need to know about spring motion in a nutshell. That's what could be on there. Let's see. Okay, so on homework 17, number 5, let's take a look at that real quick. I guess that'll be the last one we have time for. Let's see. Let me get that loaded up. And by the way, if you come up with any other questions, feel free to email me. I'll be checking my email throughout the day. So I'll be happy to answer any other questions you come up with. Let's see, number 5. Let's see here. Yeah, so for this one, oh, we have a quick question. Do you have to remember the Newton's cooling law and other stuff from lecture 10 and 11? So there won't be any lecture 10 stuff at all. And lecture 11, all you need to know about is the springs. They may have also talked about like the electrical engineering equivalent with like resistance, inductance, LRC circuits. Don't worry about that. That's not going to be on there, even though that works the same way as the springs. It's just the only application you could see on there would be the springs from lecture 11. So that's the answer to that. But let me answer this one question real quick about the Cauchy-Euler equations. So for this one, they give us y double prime plus 13 over t y prime plus 35 over t squared y is 0. So at first it doesn't quite look like a Cauchy-Euler equation because I said that the powers of t need to match the derivatives. But what we could do is we can multiply both sides by t squared. And so we have t squared y double prime plus 13t y prime plus 35y is 0. And then this turns into a nice Cauchy-Euler equation. And then we could just use the polynomial for this. So this one would be r squared. And then don't forget for the Cauchy-Eulers, it's a little bit different from the middle term. We have b minus a. So 13 minus 1 will be 12r. And then plus 35 is 0. So we would just solve this polynomial, and those would be the powers of t. So I think if I see this correctly, this will factor into r plus 5, r plus 7. So we get r is -5, -7. So those will be our powers of t for this one. So the moral of the story is, yeah, even though it doesn't look like a Cauchy-Euler equation, it's still going to end up being that way. So we have minus c1 t to the -5 plus c2 t to the -7 right there. All right, what do you do if you have t less than 0 in that equation? It's essentially going to be the same thing. You really only need to worry about those when you have natural logs. In those situations, you need to place the t inside there with a negative t, so you don't have a negative number inside the log. So the t being less than 0 only matters if r is an imaginary number. In that case, you just stick a negative t or an absolute value of t inside your log, and that's all you have to do for that. So that's usually not a big deal. All right, guys, it looks like I'm out of time for now, but yeah, as I just said a few minutes ago, feel free to email me any questions you have, and I'll be happy to help you guys out. So yeah, let me know if you have any issues tomorrow on the exam, and I wish you guys the best of luck. Hope it goes well.